About 35 years ago, a forest health specialist named Johann Brunn was walking through the forests of the Pacific Northwest on an effort to plant red pine trees. Mr. Brunn was trying to expand the red pine population, but he found that his planted trees kept dying. Upon further inspection, it was discovered that the cause of death was a honey mushroom fungus called Armillaria gallica. Mr. Brunn took some samples of the fungus back to his lab, where he and his colleagues soon realized that the fungus was massive and extended an unknown distance across the forest. In 1992, after close to 3/4 of a decade of research, they published some of their initial findings, having calculated that the mushroom was at least 1,500 years old, with a biomass around 11 tons. This was their conclusion in 1992. Except, at that time, they hadn't actually found the edge of the giant fungus. By the time they did find its edges, they realized that the fungus was nearly 1,000 years older than they thought originally, and more than 4 times as large. So, while this so-called humongous fungus, yeah, that's the name they gave it, while it will regularly sprout mushrooms that will live for a season and then die off, its greater body mass, its total mycelium that exists under the surface of the soil, that greater mycelium has stayed alive for 2,500 years. Mr. Brunn said, quote, "The defining feature of an individual is its unique genetic code that defines the rule set for its continued existence. In this sense, the cell lineage of the humongous fungus dates back to a single sexual mating event roughly 2,500 years ago that defines its way of life." Unquote. This is interesting because it's not all that easy to live for so long, especially if you're a giant organism with uncountable trillions of cells. All of that cellular growth means a lot of cellular replication, and all of that cellular replication should put the organism at risk of cancer, because of the sheer probabilities of cancerous mutations arising. Ultimately, all of this cellular replication should put the organism at risk of widespread cancer and eventual senescence and death, but apparently not for this fungus. The question that Johann Brunn and his colleagues addressed in their most recent paper, published in the Proceedings of the Royal Society B, is, how does such a large fungus persist for so long? In a nutshell, they did some genetic screening and some analysis, and they found that its genome is remarkably stable and resistant to mutations. Mr. Brunn said, quote, "It turned out that this fungus, this clone of Armillaria gallica, has an extremely low rate of mutation," unquote. He continued the point, describing the fungus as being representative of the opposite of cancer, as cancer cells have wildly unstable genomes that cause them to grow into tumors, whereas this A. gallica fungus has this really stable genome that has allowed it to safely perpetuate itself for more than 24 centuries. One of Mr. Brunn's colleagues described the fungus as, quote, "a very persistent organism with few mutations," unquote. So all of this is really interesting. They found that the fungus did have somatic cell mutations that had slowly appeared as it grew and spread, but that the overall rate of mutations among all of its cells was actually really disproportionately low. Whatever genetic traits it has that allowed the fungus to persist for thousands of years without developing numerous cancers, or malformed tissues, or a cellular dysfunction that would have impeded its growth, diminished its health, and ultimately led to its death. Thanks to its genome, it persists in a healthy manner, continually growing across more than 190 acres of Pacific Northwestern forest, and opportunistically feeding on sick and dying trees, just like any happy parasitic fungus would want to do.